Good morning. It's my pleasure to participate in this session about the FEDeRATED project, and I will be presenting to you the progress of our semantic modeling group and the work that we do and why we do that and what these models are for. I'm the chair of this group, which is one of the most interesting things I've done in this project. In my day job, I'm also the head of digital cargo at the International Air Transport Association, and there I look after very similar developments, but focused on the air transport mode. So let's get started on this one here. Firstly, why are we doing this? What is the challenge we're trying to solve? If you look at the work that you're very familiar with, which is the work on PI, which is essentially about creating this global logistics network and benefit from the efficiency of connected services and everything that goes with that and everything that connects it. One thing that a lot of companies are focusing at the moment is actually around APIs, which is a way of connecting the computer systems or the IT system that these companies have. And so if the first objective around PI would perhaps be to create a logistics network, the work being done on API is around creating digital networks. And then if you sort of move to the right, once we have that sort of connectivity, the big question is what are we going to do with it? And of course, what we do with it is exchange data. So ultimately, what we're trying to achieve is ways of exchanging data with other parties, getting insight into the data of other parties, get transparency, visibility, but also derive some knowledge and value from that data. And so it's the area on the right that we're focusing on here. In my work at IATA, we're doing very similar work around the One Record project, and there's also the other activity of which also is a session here at this conference around the Internet of Logistics, and in that session we'll explain very similar things, but of course it's a slightly different focus. Moving on. One of the things that is worth mentioning is that I sort of jokingly played around with the A, the P, and the I, as you can see here. They're not really related. It was just something that I noticed. But the work around data and AI is very, very closely related. Often these days when we think about AI, we think about things like machine learning. But actually, a lot of AI work that was done before machine learning is from a very different nature. And all of that starts with data models, which relate to what we call semantic models, which is more about the context and meaning of data. This then leads to an ontology, which is essentially the description of that. This very narrowly links to knowledge graphs, where we capture data and understand how it relates to other data via that ontology. And that then leads to artificial intelligence, because once you have a knowledge graph, you can query it and learn things about the environment of which you have received data. Okay, so you can see that link there. One of the things that needs to happen and is happening in the moment is around how we view data. Back in the old days, maybe the days of COBOL and that sort of era, we only were concerned about writing computer code that was able to generate documentation. We then abstracted the information in that documentation into something that we call data models. And then the code interacts with these models. And so that's where we more or less are today in terms of the bulk of the systems, but also the bulk of the standards. So a lot of the data standards that are out there are actually based on that concept there. Right now, there is a move to go and sort of abstract even more, away from the code and away even from the data models into something that we call ontologies. And ontologies, and I'll be talking about it a lot more during this session, allow us to create data models. So we still have the data models, but actually we have a way of describing them using ontologies. And what is neat, and I just said that, there's a very direct link between ontologies and knowledge. And that is something that in the era of AI is something that we absolutely care about. So, a couple of years ago, as the FEDeRATED project started, we realized fairly quickly on that we needed to do something about how to integrate all of those data models from the various transport modes. Because ultimately, FEDeRATED is about creating interoperable systems across the various modes. And so we need to do something about data. And so we agreed to create the semantic modeling group, and the objective of that group was to essentially integrate the existing models and standards and even ontologies where they exist in such a way that federated semantic model could act as a go-between, if you want, a common and uniting model. And I will talk about how we do that, but that was really the vision here that we're trying to implement. And so the way that we do this, or we did this, is we first took a number of data models, and we sort of, from the various modes, air, road, maritime, and rail, and we used that to create a first draft of that semantic model, that federated semantic model. But as you can see, not all the travel modes are there, transport modes are there. And so we now go to the next step, which is where we then validate that semantic model that we created and try and map it to third-party data models or even ontologies and figure out whether or not this works. And if it doesn't, then obviously we have to fix something. Or if it does, then, we get a tick box that we're on the right track here. And then lastly, since Federated is a large project with a large number of living labs or pilot implementations, we now use that semantic model to make sure that these various implementations actually are based on that semantic model, or if not based on it, at least are able to align or map to it. Then in theory, we should be able to interact with any of these living labs without further ado. So that's sort of the underlying objective here. So what is this semantic model that I'm talking about? At the highest level, what you can see here is that there's a certain number of concepts, right? It's about semantics, it's about concepts. All of them you know. You've heard about transport means like, airplanes, trucks, ships, you name it. Goods, we have products, we have the notion of equipment, but we also have sort of the business and compliance type things like legal or natural person or a customs item or a business service. And then lastly, we have the concept of a physical infrastructure around nodes and hubs and places. And so when you put all of this together, what you see is that in the center here is the notion of an event. And an event is actually what connects any of the two bubbles. Okay, and so that is sort of the high-level model that we developed. We broke this into 5 modules. I say us. In fact, we've had a lot of support from the Living Lab in the Netherlands, with support from TNO, the Research Institute, and I have used some of their material as well, and I appreciate that and thank them for it. So they structured this ontology into 5 modules. You can see them on the left there. And so if we sort of zoom in, what you'll see is that these 5 modules have relationships between them. In fact, there is the 5th model I didn't mention is something we refer to as classifications, which is essentially code lists. Okay, there's no transport and logistics without codes. We all know that. But if we just put it on the side, what you then can see is that each of these digital twins and physical infrastructure and events and business services have a structure inside them. Okay, so we've structured it like that. And rather than try and read that, which I'm not even sure is physically possible, let's just zoom a bit more. And for example, here we'll look at the logistics twin of the digital twin. And so what you can see here is things again that transport means equipment. For example, if you look at equipment, you have containers and trailers, or if you look at products, it's the products that we ship, like bulk product or consumer products, etc. And so as you can see, we sort of can sort of zoom into this semantic model and learn more about what are the semantics, what are the concepts that are happening inside logistics and transport. And one thing you have hopefully noticed is that this is indeed not mode dependent. Any of these words I've used, any of these concepts that I mentioned are used across the various transport modes. There may be some dialect, some words may or may not mean exactly the same thing, but that's fine. And not all of these things exist in every transport mode. But again, that's fine. The model will cover it all. Now we have a similar level of detail for all the other ontology components. If I go one step further, I now enter in the code, right? There comes a point when PowerPoint doesn't work anymore and you really need to sort of start digging into it. And so here, for example, I've just taken just a piece from the events ontology. So here, for example, I've sort of put some lines around the event, the arrival event, and actually there's description of that there. And as I mentioned before, in fact, events are links between two other things. So in this case, an arrival event is an association between a digital twin type transport means and a location. All right. To put it simply, when the train arrives at the station or when the airplane lands at the airport, these are arrival events. And so, as you can see, or you can't see, but you'll have to trust me, for every component there, we have this sort of definition, which is an open source. We have this available, and this sort of creates all of these structures that are there. Okay, so that is essentially what this semantic model has led us to. Now, the question is, what can you do with this ontology? And in fact, there's a lot of things you can do with these ontologies. And I want to give a few examples for the sort of things you can do with it. And I think you'll quickly recognize this goes far beyond the current use of data models and data standards. Okay, so for example, you can use the federated ontology to align it with other ontologies. And align is a special term here. It has a special meaning in the world of ontologies, which is essentially how you link them up in such a way that they can interact. You can also use it to map it to data models, because ultimately data models is what our code interacts with, as I mentioned earlier. You can also use it to generate data models. It's very powerful, because if you think about it, if you've created the ontology and you can generate data models from it, then you only have to maintain the ontology. You forget about maintaining data models. And I'll show you some examples of that. You can also use it to generate APIs. And that's a really powerful way of creating APIs, because rather than interpreting a model and hard coding it in an API, it's all automatically generated. So think about that for a second. So now we only have to maintain this ontology, which is in a descriptive language that is part of our vocabulary as logistics and transport experts. And all of that to directly generate data models and APIs. It's pretty cool. I'll show some examples of that too. Then we can create graphs. Now, sort of knowledge graphs, for example, the KGs is the big buzzword, or if it isn't yet in your environment, it will be. We'll all be talking about knowledge graphs very soon. Knowledge graphs essentially are these sort of a graphical representation of the structure that's inside the ontology, and that contains knowledge. What I mentioned before. If we know that a container is associated with an airplane, then we can figure out, for example, the association is something like an airplane can carry containers. That tells us a lot about what a container is for. It also tells us something about how aircraft operate. So that knowledge is embedded in the relationships inside the ontology. Now, once we have that, we can go to the next step and start reasoning and querying these knowledge graphs. And now, if you think about it, the stuff you normally do with Google, you can now start doing that with your logistics environment and start asking questions about the sort of freight that you need to transport, the sort of destination, what capabilities you're looking for, and the knowledge graph will give you the answer. So it's really a very nice progression from something that originally was just a data model, or even before that something was captured in documents, to something that our modern systems can interact with automatically, okay, without us needing to read a document. So let's look at some of here. For example, we did an interesting experiment or exercise with the European Union Agency for Railways, where they have actually implemented or created their own ontology, their own knowledge graph, and they have a really nice application because they also have all the data that goes with it. So when you look at that system they have developed, which again is based purely on an ontology, they can query the status of the railways, they can query the status of the trains that are running on them, and anything you want to do in that environment. Now, what's interesting is that if you now go to the left and you look at the federated ontology, the federated semantic model, what you may have picked up from my earlier slide, that it's actually relatively high level. It's really about location, a business contract, equipment, it's sort of the high level language of logistics and transport. Whereas if you go into the European Union Agency for Railways ontology, ERA, you will see that there's a lot of detail in there. You can find out the information about the gauge, you can find the information about disruptions and incidents that may have taken place. None of that actually exists in a federated environment. So essentially, when we're talking about aligning ontologies, it does two things. On one hand, we compare that the models see how they compare, but also how they relate to each other. And so what you could imagine here is that if you align your ontology, or in this case, the federated ontology, with other ontologies, you're creating an ever-expanding network of knowledge and concepts about logistics and transport in very, very specific special areas. So this is something that grows. What I personally like about it is that the ERA have done all of the work without necessarily knowing that federated ever was going to exist. In the same way that the work we're doing at IATA with the One Record project, where we have an ontology for air transport, I sit down with air transport experts and we talk about what happens inside airline operations, okay? The people at ERA have no idea what we do at IATA, and nor do we have any idea what they do. It doesn't matter. We are the experts in our domain, they are the experts in their domain, and when we take these two different domains together and we align them with the federated environment, what you now get is a very large body of knowledge that's been constructed by various different agencies and entities that all put their knowledge about their semantics, about their semantic models together. Okay, so that's really very, very powerful. You can also sort of take this really to ground level, I would say, and integrate an ontology like federated with a system like TradeLens. Okay, so the exercise that was done here was to take the TradeLens data model, which was, I think, exported into a CSV file just for convenience. This was then taken into federated in an RDF file, which is the common format for ontologies and semantic models, and then used to see if we could map that. And by mapping it, we could then make sense of the data that comes out of TradeLens. You know, that's a one-off exercise. Once you've done that, you can start pulling in data from TradeLens, and as you'll see a little bit later, you can push it out into another data environment. Okay, so mapping is not the same as alignment. Mapping is really about how you transform data from one format to another, whereas alignment is about how you connect different ontologies. Okay, I hope you can see the subtlety here. Now, as I said earlier, you can use ontologies to generate data models. So the example I'm showing here is actually from a different ontology. It's the One Record ontology that the airlines have created. And you can almost sort of, you can follow just from the description of this thing, that there's the One Record ontology. Okay, it's a working draft because it's the latest version. What you can then see is that we have an ontology for the API, which generates JSON LD files. JSON LD is JSON linked data. It's a JSON format, but it is a special dialect used for linked data, which is something that's very useful in semantic models. And then we use that to create some what we refer to as cargo-related models, such as, for example, CO2 calculation method.json. And if you were to go down, and I won't do that in the interest of time, what you'll see is that the entire file structure is directly generated from that single One Record ontology, which is pulled out one part, which is the CO calculation method class. Okay, and so that's really powerful. That's really powerful, and it's actually the way we use it is that, as I said before, we maintain the ontology and we generate 50, 60 different data models for different things that we want to do with that without human intervention, which is pretty cool. Similarly, and equally powerful, if not more so, we use exactly the same model, exactly the same ontology to automatically generate APIs. So what you essentially have is that you have a description of the data in the semantic model, and you can use that, like I just said, to generate data files, but you can also generate that to create an API which has all the constraints that go with your semantic model. So for example, if the semantic model defines that, I'm making this up here, but that, for example, an airway bill needs to have a shipper's address and a consignee address, then the generator will actually take that constraint, and when it creates the API, makes that requirement in such a way that when you submit the data to the API, it will check that the right data elements, in this case a shipper's address and a consignee address, are actually there, and if not, it will generate an error and send it back and say, sorry, your data your data submission is badly formatted, it misses these and these elements. And so again, that is a completely automatic generation, starting from a ontology in RDF into essentially a Java API. We have this running. In fact, what you can see here, for those that know, this is a Swagger document that goes with that API, which gives an indication of the fact that there is in fact a real API behind it. I promise you I did not Photoshop this one. Next one. You can also look at the ontology and look at it as a knowledge graph. So here I've taken, for convenience, because I had it, a graph of the one record ontology. Now, again, one record is closely related in terms of concepts with federated, so this could have equally been the federated model. But as you can see, there's a lot of things that relate to a lot of things, so actually it's just a huge mess. It's really not a very convenient way of looking at data, but it sort of tells you how things are interrelated. The sort of ontologies are not trees, they're far more complex than that. Everything relates to everything. And you could zoom in, of course, and pick something out here. I will also say that an ontology is about structure, whereas knowledge graph actually requires some data. If you don't have data, then there's not much you can query. But if you have the data, what you can do is query and reason with those graphs. And again, this is some work that's being undertaken by TNO in Delft in the Netherlands, where on the left they start with a knowledge graph, which is part of the federated semantic model. They define a query, and what they extract on the right is a subset of that knowledge graph with the relevant information. And that is very much how you interact with this sort of data. So if you're used to SQL, for example, where you can query structured data in a relational database, the way that you do queries in graphs, it generates graphs, okay? So in a sense, it has far more dimensions than you would normally expect in ordinary data queries. So you have a highly complex, high-dimensional object, like the one I just showed in a previous slide. You query it and you get another much more simple or extraction from that with the relevant components and elements in there. So it's sort of the way that you work with data is evolving and changing. So this is work in progress by TNO, a very powerful tool that you really need in order to handle the complexity. Now, everything I've told you so far may or may not be news to you. If it is not, then I'm pretty sure you'll pick up some nuances where you think, well, does this guy know what he's talking about? And no, I'm not an expert. But if you don't, you may have got lost somewhere along the way, because the work around semantic models, ontologies, and graphs there's nothing straightforward about that. And so the way that I often like to explain it is, okay, you don't have to know everything about it. You are probably, if you are into IT, or even if you're in business, but you work with the IT guys, if you look at the very left of this graph, and then just so that we're all clear, this is just an example, you may be working with an ECMR, right, with a road document in XML format, which has certain information about the shipment that you're carrying. The way that we would interact with the semantic model is that we take that XML document, we can convert it into RDF. We then run a query on that in some sort of graph database or in a Sparkle query or whatever graph query language you'd like to use, and use that in order to feed into the semantic model the information that we have. Okay. Then on the other side, what you can do is say, okay, I have some information. I want to convert it into an airway bill environment, e-airway bill in this case. And so I take the structure that's inside the semantic model, I use that to generate a JSON LD file, okay, which is the sort of the JSON format for linked data, from RDF to that. And I then go back to the airlines and I say, well, here you are. I have an airway bill in JSON LD format, and it contains all the elements that were in the ECMR, but of course with their correct vocabulary and data elements. So that's something we call the round trip. You go from one source data format to another data format, and you could go back again, of course, which would really make it a round trip. Now, what I've seen is that different people have different levels of interest in this sort of work. And so I compare this to the matrix. You remember the blue pill and the red pill story. If you're a blue pill person, then don't worry about the stuff on the right. Just think about the environment that you're comfortable with, which may well be an ECMR environment or in the airway bill environment. You may be having some maritime data in a format that you are familiar with. Could even be a legacy format. It doesn't really matter, but it's an environment you know and understand. That's fine. You can stop there. But if you're interested, you can swallow the red pill and enter the world of semantics and ontologies. And when you do that, then you get into the whole conversion to RDF, you get into Sparkle queries or other types of graph queries, and you start playing around with semantics and how these things relate. It's incredibly interesting, but it does require a little bit of investment of your time in making that work. Another explanation I'd like to give is around semantic interoperability. Again, these are examples, right? So if you don't see your organization there, don't get upset, please. It's just an example. And so again, at the very center here, we see the semantic model or the federated ontology. And what you then see, and I gave an earlier example about how we could map the syntactic model or the data model from TradeLens into our ontology via a mapping, which can be done through a GraphDB, for example. But equally, I could have done the same thing starting with IATA one record, which is also a syntactic model, or in fact it is an ontology already, so we can go fairly direct. And then there's the ERA, which is also an ontology. Again, we can go directly into the semantic model. Or we have the UNCFAC with their multimodal transport model, which is fast. And we can also map that back into the semantic model. What you get then is that at the very core of it, you can have any of these models interact with each other. And this is far more simple to do it via such a common model than try and do it directly. For example, if you wanted to have a direct exchange between the TradeLens model and the UNCFAC model, you'd have to define the interface between TradeLens and UNCFAC. You'd have to map all the data. And if you want to do the same with ERA, you'd have to then do the same with ERA. And I think if you would count the lines in your head, you'll see that from the syntactic model of one to the other, there's at least already 4 connections between them and 2 across. So you'd have to do 6 integrations. Whereas with this approach where you have a semantic model in the middle, you only have to do 4. And you'll find that if you increase the number of syntactic models or data models that you want to interact with, that number of connections increases semi-exponentially. It's not quite an exponential, but it sort of looks like an exponential. It goes up very, very fast, is the point. Whereas if you have a semantic model in the middle, which may be well extended by the alignment with the railways and with other parties, you'll find that you only have to ever do that mapping or alignment once on your side. So a very efficient way of working. Let me come back to the slide that I started with. I think that perhaps now you can see that there's a lot more to data than a data model or a data standard. There's a whole world of semantics and graphs and ontologies around this. And in my view, and I think it's shared by many people that work in this domain, this is absolutely the way forward, okay? So to use semantics to capture complexity in networks, complexity in data that represents the networks is an absolute necessity to do. And so I think that the work we're doing in the FEDeRATED project has a lot of potential. I can also tell you that it's not the only project that does, fortunately not. In fact, the companies that are working on semantic models and ontologies and graphs is probably counted not in the hundreds of thousands, but tens of thousands around the world. Companies like Google and Apple, they've done Facebook, huge amounts of work in that particular domain. And so the number of semantic models, ontologies, that can be linked together is so big that if you were to map it on a graph, you wouldn't see the detail anymore because there's so much already. So that's very much, in our view, the way forward. And I think one of the interesting questions that could be debated is how all of this links to the physical internet. But that I will leave for a discussion. So with that, thank you very much, and I appreciate the opportunity to be able to brief you on this topic. Thank you, and looking forward to discussion to follow.